Welcome to Study with Rishi, and this is 10-minute system design course where we learn any system design concept in 10 minutes or less. In this video, we will talk about CAP theorem and PACELC theorem. But before we jump on to what is CAP theorem, let's talk about where does it apply. Well, it applies to distributed system. Now, what is a distributed system? Let's understand it via an example. A generic example of a single node architecture is a client connected to application server, which is then connected to our DB server. Here, the most important part of the system is DB node or DB server. This is a single server or single node here. Hence, even if we scale the application horizontally, application server horizontally, that means we add new server but keep DB as single database. This will not be called a true distributed system. Only when we scale the DB nodes horizontally and different application servers are connected to different DB nodes, we call it a distributed system. Here, a client can connect to different DB nodes during the course of their interaction with the system and expect to get up-to-date data out of the system. How does that happen? Well, as you can see, although there are multiple DB nodes available within the system, yet they all are connected to each other. They share data with each other, keep each other updated of the data. This way, no matter to which DB node a user connects to, eventually the data shall be available with other nodes and complete system be in a consistent state. If you heard me correctly, I said two very important words. One is eventually, second is consistent state. This property of the system is called eventual consistency, where all DB nodes are expected to be in sync with each other eventually. Now let's talk about problem with the system. What could go wrong here? Well, issue occurs when one of the DB nodes loses connection with another DB node, hence won't be able to send or receive data with other nodes. This will result in a state of partition. This partition can happen due to network outages or other reasons, but different parts of the system are still functional. And this property of distributed system is called partition tolerance. This is P of CAP theorem. Now we see that the system as whole is divided into multiple parts, and this is the time to choose. See, if we keep our system available for the users to interact, it is possible that user interact and store data in one partition, then some other user connects to some other partition to retrieve the same data, and data won't be available. In this case, although our overall system is still functional, the consistency of the system was sacrificed. This is A of CAP theorem. There is another way to handle the situation, and that is by making overall system unavailable and not letting user interact and store more data during partition state, hence avoiding any chance to put system into inconsistent state. This is called C of CAP theorem, consistency. CAP theorem says that in the time of partition, we can either choose consistency or availability, but not both. Now let's take one example where I would prefer availability over consistency is YouTube-like system, where it's okay if some user do not see a video for some amount of time after it is uploaded by someone. On the contrary, if I take an example where I would prefer consistency over availability is a banking system, where an inconsistency in system might result in financial loss. As we learned that CAP theorem says that in the times of partition, we can either choose consistency or availability, but not both. But CAP theorem does not talk about the states where partition has not happened. There is another slightly lesser popular theorem, PACELC, which talks about it. Here, PAC is simply CAP in reverse, means the same. After it, E stands for else, L and C stands for latency and consistency. It says in case of partition has happened, you choose between consistency and availability. But if a system is intact, there is no partition, then we choose between latency and consistency. Let's say there is like one master node and two slave nodes in a DB cluster. Here, when we interact with the master DB node and system then syncs or replicates the data to other DB nodes, here we have a choice. We can immediately return success to the user. Once data is written to master node, this results in lower latency, but system is yet not in fully consistent state. On the contrary, we can wait till the time data is written to all of the nodes which also keeps the system inconsistent state but results in higher latency. So this was the video about CAP theorem and PACELC theorem. If you like the video, please consider it liking it and subscribing to the channel. I am also a mentor at Scalar Academy. And if you have any questions around it about curriculum, fee structure, discount fee, I have given my detail in the description of the video. Do consider sending me a ping there. In the end, I thank you for watching the whole video. I hope you liked it.